All right, so this is the sixth lecture, I think, in the complex analysis series. Um, Last time we did Cauchy's theorem and Cauchy integral formula, and we're going to see these guys pop up again today as we prove three named theorems, or I think I'll probably only prove two of them because one of them's sort of useless. But uh, the I mean, Gamelin says so himself in the book, but he does say that the proof of that theorem is enlightening. So maybe we'll work our way back around to it at some point if we need to. But I'll probably skip the proof of that one. But anyway, we're going to start with Liouville's theorem. And the statement is like this: let F be analytic on C. So we're going to have a name for this. This is going to be called entire. So if you're analytic on the entire complex plane, you're going to be called entire. So we're going to say the statement of the theorem is let F be an entire function if F is bounded, then F is constant. This is one of those theorems that kind of showcases how strong of a condition analyticity is, especially if you extend it to the entire complex plane. Okay, so suppose F is bounded. So let's say it's bounded by M, and we're assuming that F is entire, meaning it's analytic on the entire complex plane. So let's fix some arbitrary point in the complex plane and let rho be greater than 0. By Cauchy's integral formula, we know that the magnitude of the derivative at z0 is, well, we just plug in Cauchy's integral formula here. It's 1 over 2 pi I, the integral around the circle. So let's draw a picture. Here's z0. We have a circle of radius rho, and we're integrating around this. F of z over z minus z0 squared dz. But this, of course, is less than or equal to 1 over 2 pi. The integral over the same contour, the magnitude's thrown inside. So, and now we parameterize the curve. So we set z equal to z naught plus rho e to the I theta. That's an arbitrary point on this curve. Then this becomes, well, let me also sub n this bound here. So this will be less than or equal to 1 over 2 pi. The integral from 0 to 2 pi, we have an m over z minus z naught is rho e to the I theta. So the modulus is just going to be rho squared. And then the modulus of dz, so that'll be this guy, whose modulus is rho d theta. And so at the end of the day, what we have is, well, the integrand here doesn't depend on theta, so we just pick up a 2 pi, which cancels this one, and we get m over rho. And so the derivative at z0 is bounded by m over rho. But we've assumed that f is analytic on the entire complex plane, and so we can make this rho as large as we like without running into a singularity. So in fact, this will go to 0. And so that tells us that the derivative at z0 is 0, but z0 was arbitrary. And so that means the derivative is 0 everywhere, and so f is a constant. Okay. So this condition of analyticity, especially on the entire complex plane, is very strong. If your function is bounded, then it's necessarily constant. I mean, it's just such a strong restriction. I don't know what else to say other than wow. So something to note is we do have estimates for the higher order derivatives in exactly the same way that we got the estimate for the first order derivative. So these are the Cauchy estimates, which just say that the mth derivative at z0 is less than or equal to m factorial over rho to the m times capital M, where that capital M is the bound on F. Okay. So again, we get this just from Cauchy integral formula, the derivative, mth derivative version. You do the same, I want to call that the triangle inequality, because the integral is basically a sum, right? This guy. And parameterize again, and it all works out the same. Okay. So here is an exercise in Gamelin that I thought was interesting. Let me figure out how to write it in a short way. So suppose you have a function f on the complex plane. We call it doubly periodic if f is doubly periodic if there are two periods, w0 and w1 of f, that do not lie in the same line through the origin. So if this is w0, here's the line through the origin. We don't want w1 on this line, so we put it somewhere else. So in other words, we have a w0 and a w1 that are linearly independent. Over the reals, I should say. And we have that f of z plus w0 is f of z plus w1 is f of z. And this is for all complex numbers, z and c. Okay, so we have two periods. So these are just numbers which we can tack on to the argument here that leave the function, the evaluation of the function invariant, right? So f repeats after omega naught, but it also repeats after omega 1, and these are linearly independent in the sense that, how do I say this better than linearly independent over the reals? I don't have a better way to say that. Okay, so here's a claim. The only entire function that, or I should say, the only entire functions that are doubly periodic are constants.
Well, if you want another way to phrase what you were saying, you could say well, I'm going to say it wrong now, but it partitions the plane into a lattice.
Yes, yes, yes. That's a very good way to say it. Um, okay, so I mean, I think the idea the idea for this is probably pretty clear. We can draw. I'm gonna pick a W0 and W1 that are a little more convenient for the drawing. So we can draw these sort of vectors that go to W1 and W0, which are just the line segments between the origin and the respective points. Okay. And another point here, W0 plus W1. And we trace out this parallelogram. Oops, sorry about that. And the value of the function in this parallelogram, well, these are the only values that the function will attain, because when you move outside the parallelogram, suddenly the function just repeats somewhere else in here. Okay, so what we want to do is we want to prove that these things are constant. And so what we're going to do is we want to apply Liouville's theorem, but we don't have to show that the function is bounded on the entire complex plane. We only have to show that it's bounded on this parallelogram because it repeats elsewhere. And so,
Which you get automatic, right? Because it's just compact continuous function on a
yeah,
compact.
yeah, that's essentially the argument. So F entire implies F is continuous on the compact set. I'll just say the compact parallelogram. And so F is bounded. And that's it. I mean, F is bounded here. It repeats elsewhere. And so it's bounded on the entire complex plane where we assume that F is entire. That's all we need. So by Liouville's theorem, F is constant. Cool. So correct me if I'm wrong, but I think these doubly periodic functions are interesting in number theory. Um, they show up in like modular forms or something like that.
That's right, yeah.
Yeah,
Victor was very into it for a year there.
yeah. I remember his seminar got canceled by COVID. Okay, so the next name theorem that Gamblin talks about is Morera's, which I hope
So
I'm.
actually, I don't know if you've met him, but Ken was doing a complex course last year,
Yeah.
and he was focusing. I presume you're doing you'd be getting that that introduction from the Stein and Stokarczyk book,
Hmm.
because they've got an exposition towards the back. So yeah, Ken McLaughlin was doing a course following that portion of the book, which is interesting because it turns into special functions, complex, it's complex special function theory.
Yeah, yeah, yeah. I need to take a quick peek here at the table of contents. How far down is that? Yeah, yeah. In the third part of the book, which we wouldn't touch for a long time.
Yeah, it definitely gets in the weeds a bit.
Yeah, yeah,
It's not as it's elegant, but it's not as elegant as the main theory.
yeah, yeah, yeah. Okay, all right. Um, so we also have Morera's theorem, which actually is very useful. Let f be a continuous function on a domain D. So the thing to note here is we're only assuming continuity. If the integral, I'll tell you what R is in a second. So if the integral over the boundary of this region R is 0 for every closed rectangle R contained in D. D is the region we're assuming continuity in, with sides parallel to the coordinate axis or axes, then F is analytic on D. This is a very nice theorem. You start by only assuming continuity in your function, and somehow by evaluating these integrals of your function along the boundaries of rectangles in your domain, you can prove that your function is in fact analytic. So let's see how that goes. So we're going to assume that D is a disk centered at Z0. And we can do that because, well, I mean, domains are nice enough that we can always sort of break it up into like overlapping disks, and then apply the theorem to one disk, and then move on to the next disk, and so on. Right? So we might as well just assume that D is a disk. So we'll assume D is a disk centered at Z0. And we'll define the primitive function the same way we had before, where I have to tell you what that contour is. So where the path, or I'm just going to call this the contour, path of integration is too long to write, runs along a horizontal line and then a vertical line. Don't know why I wrote all that out instead of just drawing you a picture. So if you have Z0 here, and let's say Z is up here, our contour looks like this. Okay, well then we're going to go ahead and differentiate by hand. We have f of z plus delta z minus f of z. Well, this is going to be, so let me expand on this picture. How about that? Give myself enough room here. Okay. So f of z plus delta z, that integral is going to be from z0 to z plus delta z. So it's going to be along this path, this contour. And then f of z, that integral is going to be from z0 to z. That's going to go from here to here. But since we're assuming that f is, this little f is analytic, or, oh, sorry, wait a minute. Yeah, we're assuming that the integral is along the integral along the boundary of any rectangle with axes parallel to the sides parallel to the axes is equal to 0. And this is one such rectangle. And so the integral over this rectangle is 0, which tells us that the integral along this contour is equivalent to the integral along, oh, I drew this backwards. This should have been this contour. Okay, that means that the integral from here to here is equivalent to the integral from here to there, to there, to there. But we're subtracting away the integral from here to here. And so we're left with the integral from z to z plus delta z, f of zeta d zeta. where this guy is just the horizontal line. I'll draw another picture down here from z up to z plus delta z, like so. Okay. And now we're going to do a little trick. We're going to add and subtract f of z inside the integrand. Okay, and I'll split this up into the integral of f of z d zeta. So that's going to be f of z delta z, right? Because the f of z doesn't depend on zeta. And so I'm just integrating delta z from z to z plus delta z. Plus the integral from z to z plus delta z of f of zeta minus f of z zeta. Okay, now the length of the contour from here to here, so this contour that we have left is at most twice delta z. So we can figure that out from well, splitting it into real and imaginary parts and then calculating distances, right? But this is bounded above. Let me call this gamma. The length of gamma is less than or equal to 2 modulus delta z. And so what we have left now is, I'm going to go ahead and divide by delta z and subtract the f of z. We're trying to get an estimate of this guy to show that capital F is differentiable. Well, then this guy is less than or equal to 1 over the modulus of delta z. So I'm using this guy for f of z plus delta z minus f of z. Right? So I'm dividing by the delta z, and what I'm going to get, so I divide by the delta z and I get this f of z, which this guy cancels, right? And I have a 1 over delta z here. And so what I'm left with is the integral from z to z plus delta z, the modulus of f of zeta minus f of z, modulus of delta zeta. And this is less than or equal to so less than or equal to 2 m epsilon, where m epsilon is the maximum over zeta of zeta minus z. Wait a minute. That should definitely be a f of zeta minus f of z. I think, epsilon. Okay. So this is the maximum of this guy over the disk of radius epsilon. Right. Okay. And now, yeah, so we insert this bound here. This is less than or equal to m epsilon, and then we integrate, and we get a modulus of delta z here. Wait a minute. No. Okay. So less than or equal to m epsilon, and then we integrate, and we know that the length of the contour is bounded by 2 delta z. That's what it is, right? So we pull the m epsilon out, and then this is the length of the contour is left, and then those delta z's cancel, and so we get 2m epsilon. Okay, good. Thought I had written something bad for a second. All right, so, but f is continuous, and so m epsilon is going to go to 0 as epsilon goes to 0. And this tells us that capital F is complex differentiable. And it also tells us that its derivative is indeed f of z, but since f is continuous, that tells us that capital F is analytic. And so that tells us that f is the derivative of an analytic function.
Sorry, so it's not. I don't think it's not f being little f being continuous tells you that big F's. It's being complex differentiable implies that well, you
So,
already did the regularity result. So being complex differentiable implies C infinity. Yeah, implies
so
analytic.
it's true, but we haven't proven Gorsat's theorem yet. That's actually going to be next.
Oh, okay.
Yeah,
Sorry.
yeah,
Okay.
yeah. So it is indeed redundant, right? Uh, that's the theorem that I'm not going to prove today.
Um.
But
Uh,
I'm going to mention it, right? But
well,
so
wait. Sorry. I meant don't you get it from the Cauchy integral formula? So for the Cauchy integral formula tells you that holomorphic functions are automatically C infinity. So once you've shown that capital F is holomorphic, you automatically have that as analytic without having to refer to little f.
I think
Because in the Cauchy integral formula, you can differentiate under the integral sign with respect to z.
mhm, mhm.
And so when you do that on both sides, you get an integral representation of the derivatives. And by the yeah, it's so you have a representation of the derivative, so it
Yeah,
exists.
yeah.
So it's differentiable. Yeah.
So there is some slight technicality somewhere in here that we can dig for if we want to later. Um, but it's probably going to take me a little while to recognize it. But I think it has something to do with the original definition of analyticity, also assuming that the complex derivative is continuous.
Cool.
Right? And this point about okay, all right. Let me come back.
Okay, yeah, no worries, no worries. I've missed some of the setup, so definitely I might be using different
I,
definitions.
I think the problem will be resolved by the next theorem, which ironically I'm not going to prove, but uh, uh, yeah, which basically says that an analytic function, its derivative is continuous, and so the assumption that the derivative is continuous to be analytic is actually redundant. Um, okay, but anyway, so this lowercase f is the derivative of an analytic function, and the derivative of an analytic function is analytic. So that means that f is analytic. Yeah, we should definitely come back to that and try to pick out, where the technicality is.
Yeah.
Okay, so what is this theorem good for? It's good for proving theorems of the form if the integrand depends analytically on a parameter, uh, then so does the integral. And an example of this is the following theorem. So suppose H TZ is a continuous complex valued function and it's defined for t between a and b and z and d. So if for each t, h of tz is analytic with respect to z, then this function capital H, which is the integral from a to b, h t z dt is analytic on D. Okay. So here's the proof. So note that capital H is continuous on D. And let R be a closed rectangle then by Cauchy's theorem, the integral along the rectangle is 0. And consequently, what we have is the integral from a to b, the integral over the boundary or over the rectangle. I don't know if I should say rectangle or boundary of rectangle. I feel like the boundary is the rectangle, but I don't know. Semantics, I guess. Okay, yeah, so we integrate 0 when we get 0. Okay, so from this point, what we do is we parameterize the sides of the rectangle or the boundary of a rectangle, however you want to say it. And what it does is it converts the integral into a sum. So parameterize integrals over the boundary. And what this does is it gives us 4 integrals of a continuous function. And what we can do is due to the analyticity of H, we can go ahead and swap the order of integration here. And this gives us that this guy, well, this is equal to 0, but it's also equal to the integral over the boundary of the rectangle, h of z, because that's what this guy is. And then from here, we just apply Morera's theorem. And that gives us that this guy is analytic. Okay. So let me move on to another exercise, which is not hard, but I thought Christoph might like because it reminds me of Ramanujan's master theorem. Let h be a continuous function on the interval a to b. So this is An exercise in Gamelin's book show that the Fourier transform. So we're doing a finite Fourier transform here. Is entire and satisfies the boundary condition. And this is for z equal to x plus iy. Let's see. Oh, and for some AC greater than 0. So functions that are entire and satisfy this bound are called entire function of finite type. And something very, very close to this is an assumption in the hypothesis of Ramanujan's master theorem. We assume that we have a power series with coefficients, and the coefficients can be analytically continued to some kind of, well, it doesn't have to be entire, but some kind of analytic function in the right half plane, I think, satisfying a bound very similar to this. And so I think that's something we might want to look into at some point. There, uniqueness of these things is pretty easy to prove, but the existence, it turned out, was harder. But maybe the Fourier transform can help us. But anyway, so proof's not very hard. Fix the t, then h of t e to the minus I t z is analytic in z because the exponential is, or I should say entire, maybe. The exponential function is entire. And this h of t doesn't change that because, well, it only depends on t. So by the last theorem, uh, I see. Okay, sorry. I messed up in my notes. I had not yet said that the exponential was entire, but it definitely is continuous in z. And then we can conclude that it's entire by the last theorem. So the last theorem, h is analytic for all z. Okay. I might come back to that in a moment. I'm not entirely convinced yet. All right, but now I know it's some simple argument like that, but let's get this bound. So h of z, capital H of z, is defined like so. This is less than or equal to the integral from a to b, magnitude of h of t, magnitude of e to the minus I t z dt. And this is equal to the integral from a to b, magnitude h of t. And then this is e to the minus I t x plus ty, where I'm using this notation, z equals x plus iy dt. And this is the integral from a to b, magnitude of h of t, modulus of the complex exponential is 1, So we're left with e to the t y. Yes, okay. Dt. And so, well, uh, we let a be the value of t maximizing e to the tz, not zy, e to the ty on the interval a to b. And so we have that h of z is less than or equal to e to the a. So I'm going to put this absolute value of y here. That value that maximizes this guy could be negative, in which case we have to do some absorbing of signs, right? But yeah, whatever sign I need to, I'll absorb into this a times the integral from a to b, magnitude of h of t dt, and I just take this guy to be c. Okay. So it is clear to me that this guy is analytic in Z just by looking at it because I just have this exponential here. For some reason in my notes, I wrote something to do with the last theorem, but that's necessary. Is using that last theorem, I'll have to make some argument about integrating over rectangles, and I think that would complicate things.
Yeah, so it's a bit, it amounts to the same thing, I think, because usually the point with these things is that the dependence on z is relegated to a simple function that you know is
Yeah,
holomorphic,
yeah.
and you can justify using like Leibniz integration rule, or I don't remember what they're called, for why you can differentiate under the integral sign. So using that, you get that you construct this h function, you get that it's holomorphic. Because it's holomorphic, you know it's continuous in C infinity.
Mm-hmm.
Um,
Mm-hmm.
but so if whatever you did, and if it was the same proof you just did that you're referring to, yeah, it probably all just goes through quite well, because instead of what in the last one you had a different relegation to Z, but here it's an exponential.
Right. Okay. Yeah. So if all else fails, if we had to, we could redo the entire proof of that thing, and you know, everything would work out just the same. Um, I guess for now we'll just be happy with getting rid of this nonsense and understanding that the exponential is analytic. Okay. So I just want to mention a couple more results. Uh, the first is Corsat's theorem. I again hope I'm pronouncing correctly. If f is complex valued function, c valued on a domain D such that its derivative at z0 is the limit as z approaches z0, c minus f of z0. Probably did not have to write this out again, such that this guy exists at each point z0 of d, then f is analytic on d. So I think this is having not stated this theorem yet is the reason that I was talking about the continuity earlier. when you brought it up, Alex. So, and the definition of analyticity that Gamelin gives, he says it's complex differentiability plus the continuity of the derivative. But Gorsat's theorem tells us that extra assumption of the continuity of the derivative is in fact redundant. All you need is the existence of the derivative.
Oh yeah, the existence of a primitive, yeah. Uh, or sorry, yeah, the existence of a derivative. I see what you're saying.
Yeah. So we hadn't yet gotten to that, which is why I think I had to argue about the continuity. But
That's why you had to reference the continuity of F. I see. I
yeah.
see.
Okay. So here's a quote from Gamelin's book. I'm going to write it out in all of its glory. So it's only a two-liner. So Gorsat's theorem is a useless, or is actually as useless as it is aesthetically pleasing. So in all practical cases, when you go to prove analyticity, um, you prove the existence of the derivative, and then from that point on, it's just kind of obvious that the existence, or that the derivative that you just computed is in fact continuous. And so the theorem isn't really good for anything because it's usually clear that the continuity holds. The only exercise in this section is find an example where this isn't the case. I don't know if anybody's ever done that. I think it's a joke exercise, but he does say that the proof is enlightening. Um, I don't have all the time in the world, so I'm not going to prove it today. But if we get to a point where later on in the book where he references back to this proof, I'll go ahead and prove it. Okay, but yeah, so this theorem tells us we don't in fact have to check for continuity of the derivative. And so the last thing I wanted to mention is a formula which generalizes the Cauchy integral formula. Um, I don't know how to pronounce this guy's name. Pompey? Suppose D is a bounded domain with piecewise smooth boundary. If G is a smooth C-valued function on D union the boundary, then G of W is 1 over 2 pi I, the integral over the boundary of D, G of Z over Z minus W dz minus 1 over pi, the integral over D of, I'm going to write this in some slightly shorthand notation, dg by dz bar 1 over z minus w dx dy for w and d, where this d by dz bar is defined to be 1/2 the partial derivative with respect to x plus I partial derivative with respect to y. And I am again not going to prove this, but this time for good reason, because the proof is exactly the same as Cauchy's integral formula, except we get this extra boundary term because we assume only that G is smooth. Uh, right, rather than analytic. Okay.
So what do you mean by smooth then? Because some people mean oh, just you mean C infinity?
Yeah.
Okay.
So that's a thing we should talk about actually. So the existence of the complex derivative gives you analytic,
Yeah.
but smoothness is not equivalent to analyticity.
Well, so when I define like a taking a complex derivative, it's like in regular calculus where if something's differentiable, it's continuous. So it's the same thing in complex variables. Um, so uh, yeah, different. Yeah. So when you have these things about saying that they're differentiable or complex differentiable or holomorphic, that automatically implies continuity. And then when you have holomorphic, you automatically get C infinity because of the Cauchy integral formula. Because you have a representation of your function, and in the integral, the dependence is just on this 1 over, x minus z or z minus w.
Right.
And that function is analytic or in C infinity. So you can differentiate the right-hand side C infinity to the left-hand side C infinity.
Right. So
So as
analytic implies smoothness is clear to me, but smoothness does not imply analytic is unclear.
Well, to me, it depends what you mean by smooth. Because if I mean smooth in the complex differentiable sense, then yes, because being C1 already implies analytic. So being C infinity implies analytic for sure.
Hmm. Okay. This is something I need to look into. Let me make a note in my notes. All right. Yeah. I mean, the fact that we get this correction term here tells me that there, is indeed a difference, all right,
Mhm.
between these two notions. I need to figure out what it is. Um, it like you said, it seems like that smoothness, you know, a sub assumption of that is that we're
So
C1, and if
it
we're
might
C1,
mean
Can't
that
you use
it's
Gorsat's theorem for this?
say it again, Logan.
Gorsat's theorem. If it's smooth, then every derivative exists
Yeah, and
in essence.
that seems like it should imply analyticity.
so what it probably is that it means smooth as as a function of two real variables. It doesn't mean smooth as a function of a single complex variable.
Okay, so
Because when you're complex differentiable, you satisfy the Cauchy-Riemann equations,
yeah.
right? So they probably mean, but if you're smooth as a function of x and y, it doesn't mean you satisfy Cauchy-Riemann.
How am I going to write this? G equals U plus I V. So the smoothness would just mean that U and V are C infinity.
Yeah, or in particular as functions of, I guess you and v here, yeah, as functions of x and y. Yeah,
Right.
yeah, I think so. Yeah.
Okay, yeah, that seems reasonable to me. Uh, I can see how that would be the case. Okay, so any questions or other things we want to talk about? Go ahead and pause or stop